Hi everyone, how are you today? How was your holiday? There are only 14 people here. Hi Khalid. Thank you so much, Moyat. Yes, I think we stayed introduction to reaction in aqueous solution, but the last slides. Thank you so much. I am so fine. And I ask a question to you. Is there anyone who attend, who take the makeup or yes, makeup? Because I have no any email about the makeup, so I don't decided the date of this makeup exam, so I won't do makeup exam. Because if you want to, yes, you're right. What's the deadline for the experiments? Saleh Ahmed, I wrote the dates, the deadline. Okay, please check your mail because I wrote. Yes. And I think there is no anybody who take makeup. Is that right? I think right. Because I won't do makeup, okay? I won't. Because there is no anyone in the list to the makeup list for chemistry. Yes, we are gonna go on with the aqueous solution. Did you remember where we were? Do you remember that? I think acid base we did, and oxidation reduction we did, and I think I gave you a homework, and then oxidation and reduction agents, I think. Did we do here or not do here? Do you remember that? I think some people comes here. Do you remember? Let's check here. Just a minute. I should check my slides. Where we were? Yes, here. I think yes, oxidation reduction reaction, and then I gave a yes, it's here. Here we state there oxidizing and reducing agents. Yes, you asked something about the lab report, but after the lesson, okay, you can ask. After the lesson, I will explain your answers, okay? First of all, we did our lesson and then I explained. Yes, these are the special of oxidizing agents. We call that this is the oxidant, and the other one reducing agent. We call that this is the reductant, and these are the special of oxidant and reductant. For example, for the oxidant, causes another substance to be oxidized, and then contains an element whose oxidizing state decrease in a redox reaction, and gains electron. Don't forget that gains electrons. The oxidant always gains electrons and is reduced. And the other one, a reducing agent. This is the reductant. These reductants always loses electrons, and so they are oxidized. Contains oxidation in a oxidation redox oxidation reaction. And here let's pass other slides. That's enough of oxidizing and reducing. Yeah, as I said, this is the redox reaction. That's enough. And the other one, this is actually stoichiometric of reactions in aqueous solution. This is the titration. I think the third experiments will be like that, and then I will explain how you did these experiments, and these are any experiment that first picture is explained. There is a vinegar in it. This is not bigger. This is Erlenmeyer, we can call that. And the vinegar, a small quantity of water, and a few drops of phenolphthalein indicator are added. This is the phenolphthalein. Here the phenolphthalein, and this is the vinegar. Vinegar is the weak acids, and then we know that we don't know this is concentration of vinegar, and we know that this is volume, but we don't know any about this vinegar concentration. And then this water, this is not water actually, this is chemical, and this is phenolphthalein indicator. Phenolphthalein indicator added to a flask, and for the B here we have volumetric. Here, volumetric flask, we can call that, and we drop here. We drop. This is the sodium hydroxide. Sodium hydroxide. We know that sodium hydroxide molarite. This is the 0.1 molarite sodium hydroxide, and fill the burette. This is the burette one. This is burette and volumetric. There are some volume here, and then drop in the vinegar, but slowly added. Okay, we shouldn't catch the point of this balanced. Okay, don't forget that. And then you know here. Here there is some colored here. This is the light pink, we can call it, and then that means the acid is in excess. The solution in flask remains colorless. Okay, when you shaked this vinegar, when you drop the sodium hydroxide in it, there is some pink here, but after the shaking this vinegar, the colorless is go out. And then when the acid has been neutralized, an additional drop of sodium hydroxide causes the solution to become slightly basic. Okay, and the phenolphthalein indicator turns a light pink. The first lasting appearance of the pink color is taken to be the equivalence point of the titration. Equivalence point you shouldn't catch, okay? You shouldn't catch. So you slowly drop this sodium hydroxide in the vinegar, okay? And you will see, if you watch my experiments, you will see I drop slowly and then I shaked. There is no any colorless we get, and then when we drop again and again, we get this color, we get this pink color, and you will read how much you added from the sodium hydroxide, and then this is the important thing, because you know sodium hydroxide concentration, and then you know the sodium hydroxide dropping volume, and you don't know the vinegar molarite, but you know vinegar volume, and then you calculate, and then you will find this vinegar concentration. This is the explanation of titration. Titration is a reaction carried out by the carefully controlled addition of one solution to another. This is the sodium hydroxide, and the other one, the vinegar. The trick is to stop the titration at the point where both reactants have reacted completely, a condition called the equivalence point of the titration. Equivalence point of the titration is very, very important. If you put one more drops in the vinegar, you will catch the equivalence point of the titration, and while you doing this calculation, that calculation will be wrong. Okay, key to every titration is that at the equivalence point, the two reactants have combined in stoichiometric proportions, both have been consumed, and neither remains in excesses. In modern chemical laboratories, appropriate measuring instruments are used to signal when the equivalence point is reached. Still widely used tool is a technique in which a very small quantity of substances added to the reaction mixture changes color at or very near the equivalence point, and such substances are called indicators. Let's do an example about that. Vinegar is a dilute aqueous solution of acetic acid produced by the bacterial fermentation. This is information about the vinegar, or apple cider wine, or other carbohydrate material. The legal minimum acetic acid content of vinegar must be 4% by mass. A 5 milliliter sample of particle vinegar is titrated with 38.08 milliliter of, what's that? This is the 0.1 molar sodium hydroxide. You know that this sodium hydroxide will drop in the vinegar like that. Here, yes. Sorry, I don't do that. Just yes. Here we have the flask. Yes, like that, and then I put that sodium hydroxide, and this is molarite. I know that this is 0.1 molar, and this is 38.08 milliliters. And you will see that from the experiments, I read the volumeter in the experiments. If you watch my experiments, and here the vinegar, and vinegar volume will be 5 milliliters. And now drop one drop here, and you don't forget to put phenolphthalein indicator, like approximately 3 or 5 drops will be enough. And first of all, you will find they ask us here, does this sample exceed the minimum limit? They ask us, this is acetic acid content of vinegar will be 4%, and you have to know that this vinegar's mass, okay, for the to find here. And first of all, you have to find the sodium hydroxide mole, and then this mole and then this vinegar mole equal each other. Okay, first of all, you know that this is N sodium hydroxide. Let's here molarite is equal N divided volume, and if you have to know that here you write that one molarite and volume multiply with each other, and then but be careful here the milliliter you have to convert that to liters, so this is 1000, you have to divide it here, multiply with 10⁻3, so you write here and you have to write here, and N sodium hydroxide will be, what's that, will be please can you tell me? Yes, this is a 38.08 multiplied with -4 mole. This sodium hydroxide equal with the vinegar. Yes, and this is the equal actually, and vinegar and sodium hydroxide. I write, and then the vinegar sodium hydroxide you have to write here, and vinegar is M divided M molecular mass. Yes, and you know that here you put that one, and you know vinegar molecular weight, what's that? This is the 60, yes, gram divided mole, and if you multiply with that one, you will find, I think, can you calculate that? Just a minute, I have to calculate that one. Right here or not here? Is that okay? You calculate? I can calculate the vinegar mass will be 0.22 gram. Yes, this is that mass will be in the vinegar for the 5 milliliters, but we have to that one, if we this is the 100% will be 5 milliliters, but we have here actually vinegar here approximately like that 1.01 gram divided milliliter. That means 1 milliliter is equal 1.01 gram. So that gram, that 0.22 gram, how many milliliter we have? We have actually the same. This is the 0.22 approximately. Okay, we can milliliter. Sorry, we write here the 0.22 milliliter, and you will find that percent will be, how many will be Now, let's do that. And divided 5 and 4.4. That percent will be, yes, 4.4. And that means actually the vinegar sample exceeds legal minimum limit. Okay, like the 0.4 excess. Okay, 0.4 excess the acetic acid exceeds in the vinegar. That's it. Is that clear? I think clear. This is only you will do this sodium hydroxide mole and the vinegar mole equal each other. And then first of all, you have to find the vinegar, find to sodium hydroxide mole, and this sodium hydroxide mole equal with the vinegar, and then you will find from the from mole, and then you will find mass, and the proportion here you will do like that. Here the proportion to find percentage. I think that's clear. And for your experiments, for example, I think we use sodium hydroxide, and we use unknown titration. What's that? Is the hydrochloric acids. You know, you don't know the molarites, but you know the. I think 25 milliliters. We put it. We put in the Erlenmeyer, and then you know the sodium hydroxide molarite, you know, and you know the sodium hydroxide volume, because the volume I gave you in the video. And you will calculate here molar sodium hydroxide and volume sodium hydroxide is equal to molar hydrochloric acids and volume hydrochloric acids. Only you don't know that. You know, and you know for the experiment. Okay? I think I can explain. And this is your homework. Okay. For these subjects, that's it. Actually, this week we will do the gases. The gases, yes, I will upload it firstly. Yes. We will wait to upload. Yes. This is converting. Yes, uploaded here. Gases. You know that. What is the gases? Gases, physical, for example, the gases, physical properties. What are the physical properties of gases? What are the physical properties of gases? Please tell me about that. Please tell me about the gases. Are you there? I think you are here. Yes, physical behavior to determine the gases. What are they? Please tell me some physical behavior of gases. For example, yes, I am waiting. They don't have a defined shape. Yes, freely moving particles. Yes. What about, for example, think about their ideal gases. and this formula, what are they? The physical properties. For example, I give an example, not stable. Not stable, yes, we can say like that, but not all of these are not stable. Some of gas is stable, and for example, I give an example about that for the physical properties. For example, the volume. This is the determinant of gases. The volume is physical behavior or physical properties of gases. For example, yes, I'm waiting. What about volume? Yes, I said. What else? Say something. I give an example, volume, and then temperature. Yes. What else? What else? Go Alden. Lower density than solids and liquids. Yes, we can say that, but physical properties. For example, Kamal, can you say me? Kübra, Reyhan, Saleh Ahmet, Yazan, Hani, Uğur, Yusuf, Emre, Bulutan, Abdulbari. Yes, are you there? Please say something about the gases, physical property of gases. I said I gave two examples of that physical properties. This is temperature and volume, and the other pressure. Yes, that's right, Mariam. Pressure. And what else? Amount of the gases, for example, the moles. Yes, we can call that. Okay. Yes, they are easy to compress, but it is up to volume to shape their in it. Yes, there are four properties determine physical behavior, and these are the important things: amount of the gases, this is the in moles, the volume, temperature, and pressure of the gases. The left one, there is a yellow color, and maybe yellow, greenish yellow gas is the brownish red gas. Is that a small pool of liquid bromine, for example? The violet gas is in the contact with grayish black solid iodide here. Yes, here. These are the three halogen groups. Okay, the three halogen groups. What is that? First of all, that one, the chlorine. Okay, chlorine one, and bromine, and this is the iodide. Okay, these are halogens gases, and these halogen gases always colorful, like that. For example, for the chlorine, this is yellow. Bromine, maybe red, brownish red, and the violet here, violet gases is iodides. Don't forget that. Most other common gases, for example, carbon monoxide, carbon dioxide, nitrogen, hydrogen, all of these common gases are colorless. Okay, not colorful, colorless. And we said that the temperature, the pressure is very important for the gases or the solid one here and the other liquid one. The solid here, the green cylindric tube or pink cylindric tube, pressure is always equal Yes, the F divided A, and always pressure exerted by a solid two cylinders have the same mass. This green and this pink cylinders are the same mass and exert the same force on the supporting surface. And the tall tin has a smaller area of a contact, but exerts a great pressure. Okay, great pressure. Pressure is equal the matter carry. This is the area. Area is very important, and the pink area is very big, from the bigger than the bigger than the green cylinder. So if the area is bigger, the pressure is lower. Okay, don't forget here. And pressure is generally defined as a force per unit area. That is a force divided by the area over which the force is distributed. And for solid one will be like that. The area is very important for the solid one. Okay, for the pressure. Let's looking this liquid pressure. For the liquid pressure is very important, the high and the density is very important, because pressure is equal for liquid one. Yes, this is the force divided area, but the force is G multiplied with the M. This is the mass, is like that. This is gravity, and always the H is the high, and always this liquid pressure formula will be like that. This is the gravity. It's stable and don't change anywhere. Maybe you will go to space. This gravity is will be changed, but in the world the gravity is not changed here. And the high is very important to calculate for liquid pressure, and the density. Look at that picture. That picture, all of these columns in the field, liquid the same. So the density of liquid the same. This is the same, and the gravity the same, and the higher is the same. So these liquids pressure are the same for that one, for that one, for that one, and for that column one. Okay, this is the wider of the first one, the last one wider than the first one, but the high is the same, the density is the same because it's the same liquid, and gravity the same. So the pressure of liquid of this picture the same for all of these column. Don't forget that. Let's looking for gases pressure. The others were for solid and liquid one, but barometric pressure for gases one. The measurement of atmospheric pressure with a mercury barometer, these these blue yellow arrows represent the pressure exerted by the atmosphere. For example, for a picture, the liquid mercury levels are equal. Yes, here, look at here for the A, the liquid mercury levels are equal inside and outside. Inside in that one, inside and outside. The open end tube. Okay, this is the open end tube. So these levels are equal. For the B, a column of mercury 760 millimeter high is maintained in the closed end tube. Okay, this is a closed end tube. And C1 here, as long as it exceeds, but the same here, same higher, the same level here. And for the D, a column of mercury fills a closed end tube that is shorter than 760 milliliters. In the closed end tubes in B and C, the region above here, the region above the mercury column is devoid of air and or contains only a trace of mercury vapor. Okay, and always 1 atm is 1 atm equal 7.6 torch, and it is approximately the same millimeter mercury. This is the millimeter mercury is high, so we call that this is the 1 atm because outside and inside height like that. If we use not the mercury liquid, but if we use the water, what will be this higher? What will be? Can you think that if we don't use any mercury liquid, instead of mercury, we will use the water, what will be? Yes, what will be if we use the water? Yes, say something. I will give you a hint for that. For example, mercury density is 13 and water density is 1, approximately. Yes. Pressure will be higher. Pressure will be higher. 1 atm equal will be higher. For example, yes, that's right, because the density, this mercury density is higher than water, and water feel lots of higher that one. For example, 10 meters, like that. Let's do an example about that. What is the height of a column of water that exerts the same pressure as a column of mercury? This is the same 760 millimeter high. As I said, actually, the same question I asked to you. First of all, you have to equal this mercury and water column pressure, pressure of mercury and pressure of water column is equal each other. So you have to know the pressure for the liquid one. Pressure, you know that the high multiplied gravity and multiply this is density, and the density of water and the density of what's that? Yes, water, and it is equal with the water and the mercury with gravity. Yes, and the density of mercury. Yes, the gravity is the same, so they are going, and you know that the mercury higher, what's that? This is the 760 millimeters, and multiply with density of mercury, you know that this is 13.6 gram divided centimeter cube, and you know the density of water, what's that? This is the 1 gram divided centimeter cube, and you don't know height of water. Only you multiply that here and you will find the water higher will be 10.3 meters. And you can find like this column, glass column, okay? You can't find. This is so like a flat. Yes, this is so difficult to find like this column, like the flat. Yes, this is your homework about the barometers. And I think the ethylene glycol, they are giving to you the density of the ethylene glycol and height, and only you will find the barometric pressure only. And the second one, yes, this is not the ethylene glycol. This is triethylene glycol, and they gave the height of triethylene glycol height and pressure. Only you will find the density of triethylene glycol. Yes, this is the manometer. Manometer, like a U manometer, and there is a gases, and the other one, the other column, there is a bar. This is the atmospheric bar. If the pressure, gas pressure here, if the gas pressure is equal to barometric pressure, this is the atmospheric pressure, we can call that. There is again a mercury liquid here, and there is a gases. If these gas and barometric pressure is equal, we can call that like that. If this H means the differences of pressure, is bigger than the zero, that means the gas pressure is greater. The gas pressure is greater than the barometric pressure. Don't forget that. This is important. And the third one, the C1, if delta P, this is differences between the pressure, is lower than the zero, that means the gas is less than the barometric pressure. Don't forget that. You don't forget these pictures. For the A, equal, for the B, greater than the gas pressure, greater, and for the C, gas pressure is less. Okay, don't forget that. From, of course, than the barometric pressure. Yes, let's think an example about the manometer. When the manometer is figure 65C, T means less than. Okay, don't forget that the gas less than the barometric pressure. So you don't forget the delta P. Delta P is smaller than zero. Don't forget that. That means here the C, don't forget the pictures. Delta P smaller than zero. That means the negative one. Yes. Delta P, actually, we can call this is H. Okay, higher. Differences between the pressure, higher we can call it. Liquid mercury, they give us. The barometric pressure is given like that. The differences mercury levels like that. What is the pressure? What is the gas pressure? Okay, you know that gas pressure, P bar, positive delta P given you. What is that? The differences mercury. Differences mercury levels means delta P. This is the H. Okay, this is 6.0 8.6. That means this is negative 8.6, because for the C picture, tell us the delta P is smaller than 0. So we write here negative 8.6. And you know that barometric pressure, this is 748.2, and you will calculate P gas, and this is 739.6 millimeters mercury. That's it. Only you have to remember the A, B, C pictures. And what is that? These are for the A, equal bar and gas pressure is equal. For B, greater than the barometric pressure. For the C, smaller than the barometric pressure. Don't forget that. And delta P here for the B. For the B picture, delta P bigger than 0. C, delta P smaller than 0. That's it. Is that any question? Is there any question? I think no. I passed. This is your homework. Look at here. The same thing. Suppose that mercury level in example 6.2 is higher in the arm open to the atmosphere than the closed arm. What will be the volume P gases? For the B, the same thing. Manometer picture you will use. This is some common pressure units we will use for calculating some examples, some problems of that. The units are very, very important for chemistry. You know that from the midterm, the units very, very important. For example, some of you ask me, I do that, but this is the wrong thing because you didn't be careful about units. I will give you the mole and I will give you the molecule, but the true one is the molecule. For example, I can't remember that. For example, I put the same volume, but the different unit I will give you. But the score is the same, but units are not same. Okay, for example, the same score but unit mole, the others one molecule. You don't be careful that, so you will wrong. That's like that. Yes, atmosphere, this is the ATM, millimeter of mercury. Always 1 ATM is equal approximately that 760 millimeter mercury, and the same torch. And the Pascal, for the Pascal 1 ATM like that, the Pascal. And if you divided the force to calculate kilopascal, you will like that. And for the bar and millimeter, millibar, these are important units of the gases. So be careful about that. Be careful in the final, okay, final exam. Yes, this is the simple gas laws. First of all, Boyle laws. Boyle laws for this is constant temperature. For example, you will know that. You know that the pressure and the volume and the temperature and the moles. These are the first slide, remember? These are physical properties of gases. So there are some laws, and there are some these pressure or volume or temperature or mole, they will constant of that, and then they give the other one. For example, amount of the gases, constant temperature. the volume will be, yes, these are the constant one. For example, that's constant and stable, or and what is that? This temperature stable. Only we have that one. If we have the pressure and the volume for the gases, if this pressure is lower, the volume is higher one. Okay, this is the inversely proportional. Okay, this is inversely proportional. Don't forget that they use the volume. Okay, and then the other one, this is Charles' law. For the Charles' law, the temperature very important, and the temperature between the volume and temperature, they are compared, and always we will use the temperature with the unit Kelvin. Okay, Kelvin unit, don't forget that. For example, some examples give us to Celsius degree, but you have to convert that to Kelvin. Okay, don't forget that. Generally, you will do some wrongs about this temperature. You didn't convert this temperature, and then you will do wrong. And this is the Kelvin one. They are used, the amount of gases and the pressure fixed, constant, and then only Charles' law use the volume and temperature. If the temperature higher, the volume is higher, because while we use the higher temperature, the molecule of the gases is going on so far away, and then the volume higher, getting higher. So they are the proportional, direct proportional. Okay, this is the important thing. And the last one, Avogadro's number. Avogadro's number is proportional with the what's that, amount of gases. The volume, again we compare volume and the proportional. Volume is very important. Not only the laws, one laws, all of these laws. For example, Charles, Avogadro's, and Boyle laws always use the volume compare the other one. For example, for the Avogadro's numbers, volume compares with the amount of the gases. So they are constant with temperature and pressure going on, and then the other. For example, if the volume is higher than the amount of the gases higher than. Okay, direct proportional amount of gases, and we can call these two hypotheses for the Avogadro laws. Equal volumes of different gases compared at the same temperature and pressure contain equal numbers of molecules. Okay, don't forget that. And the second one, equal numbers of molecules of different gases compared at the same temperature and pressure occupy equal volumes. And consequently, this volume and the amount of the gases always directly proportional each other. Okay, these are important. And here, yes, volume and amount of mole, amount of gases is proportional each other. And don't forget that always and always standard CTP, standard, what's the standard temperature and pressure, that means, okay? CTP means standard temperature and pressure. These are the standards. Standard temperature and pressure. What is that? 0 Celsius degree, that means the 273 Kelvin, and 1 atm is equal always 1 mole gases and 22.414 liters. Always, okay, always 1 mole gases equal that volume. Don't forget that. Can be that can be in the exam. Yes, but this is you have to know. Okay. Yes, let's come across you. Yes, here combining the gas laws, the ideal gas equation and general gas equation. That means combination the gas laws. What are they? Three gases, three gas laws we have. This is the Boyle, Charles, and Avogadro's laws. They are combined, and we have an ideal gas formula. What is that? Remember that all of these laws have the volume compares the others one. For example, Boyle's law compares volume with the pressure, and the second one, Charles' volume compare with the temperature, and the third one, Avogadro's compare with the amount of the gases, and that means consequently like that the volume is equal the directly proportion, yes, directly proportion n and t, and indirectly not proportion like this is the p, and we have the r. That means r means the constant for the gases. So we have if we want to write ideal gases equation, that will be PV and RT. That formula comes from these combining laws. Okay, if we combine these laws, we get the ideal gas, the perfect gases we have. Yes, this is the, if we write here, this is the ideal gases formula. This is very important. And if we want to find the for R constant, always we write the P, V, N, and T standard temperature and pressure we have to write here. The N, T, and P, V, T. Yes, this is for the P, 1 atm. Okay, 1 atm, or we can call this 1 bar or 1 Pascal, we can write here. But first of all, 1 atm is good. And this is the standard temperature and pressure. The volume will be 22.414 liters. I showed you. And for the mole, always this is the 1 mole, because 1 mole equal that volume. And the temperature will be 0 Celsius degree. That means 273.15 Kelvin. If we calculate that values, we will find the R 0.08205. Yes, like that. This is atm liters divided mole Kelvin. Don't forget that. We have lots of R units. If question asks you a bar, you have to convert that. Okay, don't forget that the R units very important. For example, for the R units, if they ask us for atm, that will be like that. If they ask for bar, they will be like that, but the others also important. For kilopascal, 8.3145 kilopascal liter divided Kelvin mole. Always divided Kelvin mole. And then for the Pascal, and this is kilopascal, Pascal not like that. For Joule will be like that. Don't forget that this is so important. Yes, let's do an example and then finish the lessons. The general gas equation. Actually, they give us lots of value of that. For example, the amount of the gases for the chlorine gases, 13.7 gram, and then this is Celsius degree, 45 Celsius degree, and 745 millimeter mercury. And you have to find the volume of the chlorine gases. V is equal nRT. You know that this is T 45 Celsius degree, but you have to convert that to Kelvin. Okay, this Kelvin will be 318 Kelvin will be. And what else? This is gram of chlorine gas, but this is gram, this is the mole. You have to convert that. This is N chlorine, M divided molecular mass. You know that this is 13.7 divided, what's that? Actually, one chlor atomic mass will be 35.5. This is the molecular chlorine, and multiply with the 2, and that means 70 and 70, right? The mole of chlorine will be, what's the 0.193 mole. Okay, you will write that mole here. And what else? You don't know the volume of chlorine gases, and you know pressure of gas. What's that? This is 745 millimeter mercury. That means 1 atm. You know that. You have to know that 1 atm 760 millimeter mercury. But this you have 745 millimeters mercury. That means how many pressure we have for ATM unit? That will be 0.980 ATM. Okay, and you will put that pressure here. And for the R, you will find found this pressure like the ATM. So you know that for ATM this is 0.08206. You have to write that one because you know that, and only you will calculate. And the last one, you will find the volume of chlorine 5.14 liters, like that. Only you have some conversion and then put ideal gases formula and calculate that. That's it. Is that a question about that? I think there is no any question. Okay, and this is your homework, and we will finish here. You have some question, I think. Yes, you said to me, Abdul Bari, he didn't understand what I have to find in experiment 2, 3, 4, 5. I mean, what I have to calculate. For example, for the 2, there is no any calculate actually, but while I prepare this solution, for example, for the sodium hydroxide, I gave you 0.1 molar. How many milliliter? Do you remember that? This is, I think, Yes, milliliter, maybe. Okay. Please check your videos. You will do this calculation. For example, molarite is equal N divided 5. You know that here. You know that here. How many sodium hydroxide put in the this solution? Okay. Here you will find the mole and then you will find the mass. Okay, how many gram of sodium hydroxide you weigh and then put that. Okay, this is the calculation. For example, for the third, I explained that for the this titration, for fourth experiment, I think the gases. Yes, the gases. You have the ammonia and you have the hydrochloric acids. They have some vapor, and I will measure with the ruler. And there is a calculation about the gases, and we will do that the next week about that. For the fifth experiment, I think copper hydride, copper sulfate hydride, I think like that. First of all, I weighed with the hydride, copper sulfate, and then I heated this chemical, and this chemical loses their hydride water, and I had again the differences between masses. You will calculate. That's it. These are very, very easy to calculate all that. I think I explain, and I think you can understand. You understand? Yes. Is that clear for my? Okay. Okay. Please watch carefully. Okay, because the first. Not first, because the second experiment I catch the recording, the calculation of how we prepare this solution, for example, for sodium hydroxide, hydrochloric acids, and what else? What's the sodium chloride, sodium hydroxide, and hydrogen chloric acids, I think. Is that right? All of that. I think three solutions we prepared, and all of these three solution, how we could weight that sodium hydroxide, how much take this sodium hydroxide, how much take this hydrochloric acid, and how many sodium chlorides we took, and then put this solution. These are the calculation. Okay. Next week, don't forget here. Next week we are gonna go on from here. Okay. See you. Thank you too. Take care of yourself. Bye bye.